Well, hello everybody. Hope everybody's having a good day. Let me just do a comm check. Can you guys hear me okay? And maybe one or two of you, if you could just go off speaker go off mute for a second to make sure I can hear you.
Yeah,
Uh,
you sound good.
hear you loud and clear, sir.
Okay, good. I'm having some computer problems. I'll talk about that in a minute, but as always, I'd like to go ahead and open up in prayer, and I'll give you a sense of what we're going to be covering today. So, dear Heavenly Father, Lord, I pray that you would be working in the lives of each of the students in this course. Hopefully, as a result, as we're getting towards the end, that they've seen that this is a lot of interesting information, maybe some more insight to help folks understand what it means to be programming a piece of hardware. Pray that you would help it all to come together and help each individual to get the future employment that they would like to have. Also, I pray that you would continue to work with them in their spiritual formation, Lord, that they can continue to get more gems of understanding of from scripture, the theological concepts in which we want to be guiding our lives by, and give them interesting and creative ways for faith integration. In Jesus' name we pray. Amen. Well, it's unfortunate. The timing was terrible, but probably about an hour ago, my computer started to act up. But one of the things I told you that I try and emulate the things that I recommend that you all do is I am actually using a backup computer. It's actually a desktop Dell computer running Windows 11. So, and then since I already had my data, my documents backed up, I was able to resurrect a fairly current version of that to keep that in mind. So that's the good news. There are some things that I may not have access to. And so what I was going to do today was to treat it more like a regular lecture. And so for giving folks a chance to present, I want to defer most of that to next week, but if somebody would like to share what they have with their final project or their project 3, talking about the Arduino kit, we'll just please let me know. You can just put it in the chat or whatever is convenient, or just let me know. But what I'll do is, first of all, I'll start out with a lecture. And so let's just get a perspective to be thinking about where we've gone. And we covered a lot of ground. And I know I try and continue to build on a conversation, a short run through of these things. And so sometimes it may seem a little bit repetitive, but it's just trying to each time bring a new feel as we're getting towards these latter chapters. And so the chapter that we're going to focus on today is on chapter 19. And so this is going to be the last chapter that we'll be focusing on the central processing unit. You notice that we had a separate section that was talking about the software mostly from the perspective from computer architectures, how we engage with that, the specific instructions. Now we get into the details of what is the central processing unit, how we do parallel processing and things like that. And so we'll get into this control unit in just a minute, but I don't have the flexibility to go through this as quickly as I would like. So I wanted to show just a slide or two from the greatest hits for this section, and then I'll go to our regular things that we'll be covering for this chapter. So yeah, this is the annotation that I put here that might, when I was starting to put together this, we showed this chapter before. And so we're getting a lot of terms and this idea of super pipelined and super scalar. And super scalar is you're trying to do things in parallel. And so we have like different stages where we have little ways that we can do things in parallel. And here we have multiple pipelines. And so the whole pipeline itself is actually replicated. So that's just a quick concept that I wanted to lay out. This will be one of the slides that we'll get into as we're going through chapter 19. And so we have been focusing, you have like a higher level language, Then you have a compiled program, and now we're going to go not just at the instruction level, but try and think at this micro operational level. And so hopefully by the time that we're finished with a few minutes focusing on this lecture, that'll be a little bit clearer for you. So the things that we're talking about today is a control unit operation and microprogramming control. And so these are the things that we'll be talking about. And so we'll think about the micro operations, the fetch cycle, the indirect cycle, the interrupt cycle, the execute cycle, and the instruction cycle. And so I'll have a couple of charts that will go through these step by step, and you'll get an idea what that's all about. We'll also talk about microprogram control. So to be thinking about, we're at this lower level, how are we going to, what are those instructions? What are the controls? There's something called the Wilks control that we'll get a chance to be getting a little bit of insight in, and what are the advantages and disadvantages of all of that. We'll think of the control of the processor, the functional requirements, the control signals, the internal processor organization. And interesting, I mentioned this before, when I was in your shoes, when I was doing programming, I was actually using an 8085. And so we'll get a little bit down memory lane to be thinking about that. And then about in terms of a hardwired implementation, thinking about the control units and the control unit logic. So I do have a more detailed lecture, so I'll try and give this maybe at a higher level per se to help us to think about this. But I also want to just take advantage of some of the things here to help us out here. So what are micro operations? It's the functional or atomic, operations of the processor. So we're going to this next level down, as we're seeing in this chart. It's a series of steps, each of which involves the processor registers. Micro refers to the fact that each step is a very simple and accomplishes very little. And so maybe now that you've gotten some exposure to assembly language, you're getting some idea what that is like. But now we also, with our first project with the digital logic, and you see some very basic things, and we started to see how you can aggregate that together and make things more complicated. We're going to get a chance to see some of that here within the CPU itself. So the execution of a program consists of a sequential execution of instruction. Each instruction is executed during an instruction cycle made up of shorter subcycles. And so we have the fetch, indirect, execute, and interrupt, and the execution of the subcycles involve one or more shorter operational, that is, micro operations. So this is what I was showing here is we have this for each instruction cycle. There's things that are a lower level, and even at that level, there's something below that actually takes place for each one of those things. And so we'll be considering these one at a time to work through this. And so what is the fetch cycle? It occurs at the beginning of each instruction cycle and causes an instruction to be fetched from memory. And it involves 4 registers, the memory address register, MAR. So this is connected to the address bus. It specifies the addresses for the read and write operation. And so we have to figure out, well, if we're going to read from memory, we have to figure out where we're going to go in memory. We have a memory buffer register, so it's connected to the data bus and it holds the data to write or the last data that was read. So this is the stuff that we're going to stick into where we're pointing to in memory. We have a program counter, so it holds the address of the next instruction to be fetched. And then we have the instruction register that holds the last instruction fetched. And so those are the things that we have here. So here, I'll just go over some of this. What is a sequence of events for a fetch cycle? So we look at the sequence of events for the fetch cycle from the point of view of the effect on the processor registers. An example appears here that we're showing in the figure. At the beginning of the fetch cycle, the address of the next instruction to be executed is in the program counter. And so we see this, there it is. In this case, the address is 1100,100. The first step is to move the address of the memory address register MAR, because this is the only register connected to the address lines of the system bus. So we have A. Then moving on, the second step is to bring in the instruction, the desired address in the MAR is placed on the address bus. The control unit issues a read command on the control bus, and the result appears on the data bus and is copied into the memory buffer register, MBR. We also need to increment the program counter by the instruction length to get ready for the next instruction, because these two actions read. Simultaneously at the same time. So that third step is these steps inform into
Professor, can you hear me? I think what's wrong with your mic. See if I can do something. I'm not exactly sure. Second, let me see if I can do something here.
Okay, let me do a comm check. Is that better? Can you guys hear me better?
Yeah, we can hear you loud and clear.
Okay, well, I apologize for that. Sometimes the best laid plans don't work out exactly the way we would like. So thank you for letting me know, and I once again I apologize for that. So I'll just continue on here. So maybe just back up a little bit here. So we're getting into the guts of how things are done within the CPU, and we're getting into some of the things that we've covered before, thinking about things at the digital logic perspective and control. We went through this diagram where we talked about the sequence of events for a fetch cycle. And we'll have a couple of slides here, and you have these lecture notes as well, so you can see this, but we'll have the indirect cycle, the interrupt cycle, the execute cycle. And so we'll get a chance to be thinking about this, this lower level here that we have in this diagram of, well, what are the micro operations that we need to be doing for each one of these things? And maybe this will help to give you where the rubber meets the road in the CPU itself, what's going on. So let's first of all talk about the indirect cycle. So once an instruction is fetched, the next step is to fetch the source operands. Assuming a one address instruction format with direct and indirect addressing allowed, if the instruction specifies an indirect address, then an indirect cycle must precede the execute cycle. And so this is what I was trying to show here with the stuff down here. So if it's an indirect address, we have to find it. What is the actual address? And then we're going to stick that into the MAR. The address field of the instruction is transferred to the MAR. This is then used to fetch the address of the operand. Okay, finally, the address field of the IR is updated from the MBR so that it now contains a direct rather than an indirect address. The IR is now in the same state as the indirect addressing. In this is in the same state as if indirect addressing had not been used, and it is ready for the execute cycle. So here, there's a couple more things that we have to do if we're dealing with an indirect cycle, and this gives us an idea of what that's all about. So that's the first. Then we have the interrupt cycle. So at the completion of an execute cycle, a test is made to determine whether any enabled interrupts have occurred, and if so, the interrupt cycle occurs. The nature of this cycle varies greatly from one machine to another. In a simple sequence of events, if the first step, the content of the program counter are transferred to the MBR so that it can save for the return from the interrupt. So basically, when you have an interrupt, you want to save where you are, do what this interrupt is asking for, and then go back and put everything the way it should be. So then the MBR is loaded with the address at which the contents of the program counter are to be saved, and the PC is loaded with the address of the start of the interrupt processing routine. So these two actions may each be a single micro operation. Because most processors provide multiple types and or levels of interrupts, it may take one or more additional micro operation to obtain the save address and the routine address before they can be transferred to the MAR and program counter respectively. Once this is done, the final step is to store the MBR, which contains the old value of the PC into memory. The processor is now ready to begin the next instruction cycle. So we get a chance to see some more details of how things are done at this level. And another one that we'll cover here is the execute cycle. Because of the variety of opcodes, there are a number of different sequences of microoperations that occur. So for the instruction decoding, the control unit examines the opcode and generates a sequence of microoperations based on the value of the opcode. And so when we were doing our assembly language programming, you remember that even with like add, we could have add immediate, we can have add, there was like multiple versions of this. And so this is where some of that needs to be played out within the CPU. So if we were going to take this, for example, add R1X, which adds the contents of the location X to register R. In the first step, the address portion of the IR is loaded into the MAR. So we see that. Then the reference memory location is read. And finally, the contents of R1 and MBR are added by the arithmetic logic unit. And so here is that workhorse that we've talked about that's in the CPU for doing a lot of the operations of this programmable logic unit. Additional microoperations may be required to extract the register reference from the IR and perform and perhaps to stage the ALU inputs or outputs in some intermediate registers. So those are just a couple things that I wanted to make sure to give you some perspective. Here is a flow chart for an instruction cycle. So we have seen that in each phase of the instruction cycle can be decomposed into a sequence of elementary microoperations. In our example, there is one sequence each for the fetch, indirect, and interrupt cycles. And for the execute cycle, there is one sequence of microoperations for each opcode. To complete this picture, we need to tie sequences of microoperations together, and this is done what we're showing in this figure. We assume a new 2-bit register called the instruction cycle code. The instruction cycle code designates the state of the processor. In terms of which portion of the cycle it is in. And so there's more stuff in the tech books you can read about this. And then another thing that we have is the functional control unit and the greatest hits slide that I showed very briefly. I was just giving this picture that you can see. And so what are the functional requirements that we have for the control unit? By reducing the operations of the processor to its most fundamental level, we're able to define exactly what it is that the control unit must cause to happen. So it's a three-step process to lead to the characterization of the control unit. We define the basic elements of the processor. We describe the microoperations processor performs, and then we determine the functions that the control unit must perform to cause the microoperations to be formed. So that the control unit performs two basic tasks. It deals with the sequencing, and then it does the execution. So here's just an illustration of what that would look like. What does the control unit looks like? And so we have defined the elements that make up the processor, the arithmetic logic unit, the registers, and the data paths, and the micro operations that are performed. For the control unit to perform its function, it must have inputs that allow it to determine the state of the system and outputs that allow it to control the behavior of the system. So these are external specifications of the control unit, and so just give some perspective on what's going on here. Both this illustration here, this figure, and this table are related to one another. So if you wanted to, you can kind of go back and forth. There's like test points, if you will, to be thinking that are shown up here for the data paths and the control signals that are being utilized. So to illustrate the functioning of the control unit, we can examine a simple example. So this what we're showing here shows that this is a simple processor with a single accumulator. The data paths between elements are indicated. The control paths for signals emanating from the control unit are not shown, but the termination of control signals are labeled CI. And so that's what we have, all these different Cs that are there, indicated by a circle. And so it's like, you can think of these as like test points that you can get in there and see what's going on. The control unit receives inputs from the clock and the IR and flags. With each clock cycle, the control unit reads all of its inputs and emits a set of control signals. Control signals go to 3 separate designations. And so we have data paths, we have the ALU, we have the system bus. And so these are the 3 things that we're can lay out here. So the data paths, the control unit controls the internal flow of data. So we have that for example, an instruction fetch, the contents of the memory buffer register are transferred to the IR. So for each path to be controlled, there's a switch. A control unit from the control unit temporarily opens the gate to let the data pass. For the arithmetic logic unit, the control unit controls the operations of the ALU by a set of control signals. These signals activate various logic circuits and gates within the arithmetic logic unit. And finally, the system bus, the control unit send control signals out onto the control lines of the system bus. So this is an illustration of, you can see the internal bus within the CPU. And so this is a different way of looking at it compared to what we've observed it previously. So it's showing a variety of data paths, and the complexity of this type of organization should be clear. More typically, some sort of internal bus arrangements has to be present. And so we're seeing all these different things and how they communicate with one another. If we were to think of this in terms of parlance of a computer at a higher level, you can think like your motherboard or your system board. You plug in all these different components, and so they can be talking to one another. And so that's what we are trying to illustrate here with this internal bus. So we'll have a handful of charts to be thinking about the 8085. And so maybe one advantage for looking at something that's a little bit more historic is that it's relatively simple. And so the same concepts that have just gotten more developed over time are laid out here. And so we have a figure, and then we have a table that talks a little bit more detail. And so it's a companion for what we have. So we're looking at the 8085 organization, and so there's a couple things that I'll point out. There's the incrementer and decrementer address latch, the logic that can add a 1 or subtract 1 from the contents of the stack pointer or program counter. This saves time by avoiding the use of the ALU for this purpose. And so we see that there are a couple tricks, even for an 8085, that are starting to be implemented. There's the interrupt control. This module handles multiple levels of interrupt signals. And then we have the serial I/O control. This module interfaces to devices that communicate 1 bit at a time. So even something that here, and this is goes back a couple decades, but it's still pretty rigorous, and it has a fair amount of capability. There's a second part of this table. So just you can see that in the lecture notes that I've made available. There's a pinout for the device. And so we got a chance to be exposed to this kind of a level of connectivity when we were using our Arduino. But ultimately, if you're going to start to wire things together in the hardware, someone needs to know how things work. And so this just gives you a chance to be seeing that. And so this is the pinout. And this is actually, I know we got a couple engineers in our course. And here we have the timing relationship is like you have the clock. And so when the clock is, say like you have a rising edge, things start to clock in. And so we can be seeing some of these different things that are, you're giving a temporal perspective, maybe in a different way that we haven't seen before. So this shows for an 885 the value of internal control signals. Of course, at the same time, the control unit generates internal control signals that the control internal data transfers. The diagram shows the instruction cycle for an out instruction. 3 machine cycles are needed. During the first, the out instruction is fetched. The second machine cycle fetches the second half of the instruction, which contains the number of the I/O device selected for output. Third, during the third cycle, the contents of the AC are written out to the selected device over the data bus. The address latch enable pulse signal the pulse signals the start of each machine cycle from the control unit. So just maybe I'll just highlight a few things like I mentioned there, just to have you get a better sense of why we're talking about a timing diagram here and how that starts to come into play. So a wide variety of techniques have been used for control unit implementation. Most of these fall into 2 categories, either a hardwired implementation. So the control unit is essentially a state machine circuit. That's a term that maybe some of you have heard of, a state machine. It means that you can either be in one state or another. So if I was to use a simple example like an automatic door opener, the 2 states would be the door's open or the door's closed. Its input logic signals are transformed to a set of output logic signals, which are the control signals. And there's also a micro-programmed implementation. So we can either just make it hardwired, so it's a hardware implementation, or a software implementation. And so those are 2 possible things. This may look a little bit complicated, but we talked about muxes and demuxes. And so basically you have like a 4 inputs to a 16 outputs. So 2 to the 4, you actually have the possibility of 16 outputs. So you can be activating one of 16 possible activities with that. And so I'll just leave that high level explanation to what's going on with that chart. So for the control unit, we want to be decoding the inputs. And so we could be using this kind of a device that says, okay, based on a bit sequence, we're going to select one of 16 possibilities to be thinking of like what we're showing there. And so this is some of the activities that needs to be going on in the guts of the CPU. So by now, I think you're getting a little bit of a sense of this lower level of activity that's going on in the CPU. We talked about we can either have things hardwired, but just like for other things that were completely different, like PCIe, you have a point-to-point virtual connection that you set up for as long as you need. But then again, you can then have it go to another point-to-point connection. With a microprogram, we can actually make this more surgical and have some more flexibility in the CPU design. And rather than having it hardwired, and maybe that's a great configuration for half the time, but the other time it's not. So I'll just leave it at that higher level to introduce that idea. And so this is a term that was first coined by Wilks in the 1950s. And so this is just something that has continued to be out there that's useful for us to be mindful of. So just like we have things at the assembly language level, micro instruction, you have the same kind of format that say you have a 16, 8, 16, or 32 bits. You have to determine, well, what are each one of those bits going to be programmed for? And so we're seeing some structures similar to what we saw in assembly language. So we need to have this idea of a memory control. So it's like we're having a computer within the CPU. We're using some of these architectural ideas that we've already talked about in this course, but we're just now having it at a lower level within the CPU itself. So The control memory of what we saw in the last slide contains a program that describes the behavior of the control unit. It follows that we could implement the control unit by simply executing the program. So in this figure, we're showing that the key elements of such an implementation. The set of micro instructions is stored in the control memory. The control address register contains the address of the next micro instruction to be read. When a micro instruction is read from the control memory, it is transferred to the control buffer register. The left-hand portion of that register connects to the control lines emanating from the control unit. Thus, reading a micro instruction from the control memory is the same as executing that micro instruction. The third element shown in the figure is a sequencing unit that loads the control address register and issues a read command. So that's a little bit more specifics to be thinking about there. We also can be thinking about the functioning of a micro program control unit. So I'm going to just skip over this. I'll just maybe mention a few highlights here. This is, we can examine the structure in greater detail. And here, as compared to what we were talking about in the previous slide in the figure there, we see that the control unit still has the same inputs and outputs. And so we are now just fleshing it out, giving some more specifics. So this now just gets into this idea of maybe we have something that's hardwired, but then we can be having a control signal to say that which one of these versions are we going to activate. So this is something, of course, that has continued to be refined, but back in the 50s, as Wilkes depicted a general structure that you could have this programmability presented in a certain manner. The heart of the system is a matrix partially filled with diodes. During the machine cycle, one row of the matrix is activated with a pulse. This generated a signal at those points where a diode is present, which are represented by these dots. The first part of the row generates the control signal that that control the operation of the processor. The second part generates the address of the row to be pushed to the next machine cycle. Thus, each row of the matrix is one micro instruction, and the layout of the matrix is the control memory. There's more information in the textbooks that you can read up about that if that's something that you find interesting. So this is a table that shows the complete set of micro instruction that is expressed in symbolic form. And so basically we're moving things around, we're storing things. And so these just give some example of what Wilkes was envisioning early on for the kind of capability that we would be thinking about that. So this is the second part, so it's just a continuation of that, and so I won't go through that. So the good news about Stalling is he gets into a lot of detail, and so for when someone has seen this for the first time, that can feel a little bit overwhelming. But on the flip side, yeah, I think it can be a useful thing for us to get some perspective and to consider that together. So let me go ahead and stop and see if there's any comments or questions on what I covered. I'll stop sharing my screen for the moment. I haven't looked at the chat for a while, so let me just double check. I hope that with my phone connection, is the audio better now?
Yeah, that's crystal.
Okay. Well, once again, I apologize for the issues that I was having there. It's kind of a bummer when just about an hour or half hour before we had our meeting that I was having some computer problems. But any questions that folks have? Either on this or about some of our project work?
For the Arduino project, you want us to provide like pictures of our thing and also a video of it working?
Yeah, for me, I find that both of those serve different related purposes. And Wasim had talked about this a little bit on Tuesday as we were getting into that. And I know Enzo, I think he had a preference of having videos. And so I'll still have to make a modification so you can actually submit videos as well as the screen captures. But the screen capture is a way of how you can be showing what you did with your wiring board. Maybe if there are some simple functionality, you can be showing some pictures to show it in one state or another. And the video can actually do more interactive. I think one or two of you, maybe some of it, most of what's going on, you're just seeing it with the GUI. So you have the information that you're getting back from either the plotter, the serial plotter, or having the data that you're streaming. Those are some possibilities that you could be having. So yeah, you can include both, and that's something I'll fix later today. Okay.
Okay, cool. Also, one more thing. I noticed there's a faith integration essay assignment, but there's like no instructions about it in Canvas.
Well, thank you for bringing that up. For folks that maybe have had some other classes with me, this is something that I think is really important. And so as you start from APU, you're just starting to think of your major and have a general idea of what that's all about. With the variety of curricula that you're getting exposed to, both in your discipline as well as the general education, the biblical and theological components, you start to get an idea of, well, what is your life all about? What is your life plan? And so the faith integration assignment is to try and figure out how you're going to be integrating your faith within your future career. And so there's a variety of different possible ways in which that could look. So maybe what you just want to be is to have a good, strong ethical standing in what you're going to be doing in terms of your future. That would be certainly a really great thing to do. Another possibility, what they do is they have their career, but they also volunteer on the side. And so sometimes at APU, they have guest speakers from people in ministry or companies. And so maybe what they're trying to do is provide technological means that are going to be helping people in third world countries. That could be a second possibility. A third possibility is maybe you want to make that your full-time career, that you're focusing on those types of things, or being mindful of how is the technology or the programming that I'm doing impacting the world at large. Those are all possibilities. So those are maybe some of the big things that you could be talking about. Some of you, like Enzo had mentioned that he's applying for grad schools. And so what comes next after your time here at APU? Is it school? Is it getting into a job? It's been nice. Sometimes I hear about folks that they're getting serious with their girlfriend or boyfriend. Some people are getting married, moving to another part of the country after graduation. Trying to think of all of those things. And there was a person by the name of Goddard. I might have mentioned him before. And so when he was your age, maybe a little bit younger, when he was 15, he wrote over 100 things that he wanted to accomplish in his life. And you can actually go to a website and see that he, over that 120 or so things that he did, he had an extremely high percentage of actually accomplishing those areas in his life. And the big thing is he wrote it down. And the idea of writing it down and coming up with this plan for your life is something that's going to be quite beneficial for you. And so that's what I would like to have people to be thinking about in terms of the faith integration. Since there are multiple threads that come into that, That's the reason why I let it kind of with minimal kind of directions, but those are the things that I'm looking for people to be thinking about. Is that clear? Does that help?
Yeah. Is there like a specific length you want it, or is it just like however long we need to write?
It's an essay, and I would say that say something like on the order of like 1,500 words or so. Just throwing out a number, like maybe a couple of pages of double space text, something like that. Something that you get a chance to be thinking about it enough that you get some perspective on what it is that you really want to be all about. Okay.
Okay, got it. Thank you.
All right. Well, thank you for everybody, and I apologize for some of the computer problems. I think for the most part we were able to flex pretty well, but by next Tuesday I'll have everything back to normal, God willing. So, but if not that, I'll have a workable backup for sure. Okay. All right. Well, everybody take care. Have a wonderful rest of your day. Bye bye now.
Thank you, Professor.
Thank you.
Thank you.